Okay, one of the things that I've always told students when they give presentations is that a picture and the kind of things I just showed you give you an appreciation, but they're not necessarily the best way to give understanding on how something works. And so I'm going to go through a little bit of schematic chalk talk here to explain the actual operation of the gas delivery in particular. And so here what we have is certainly the gas tanks themselves. And on those, they go through the humidification train. And so literally the setup was designed, if you notice, it was inside these vessels. And they look kind of complicated, and they probably don't need to be nearly that, but one of the things to realize is that since this is coming from a pressure regulator here, and that pressure regulator is set to a maximum of sort of less than, if you will, 15 psi. And the reason is that we don't want to have a safety issue of pressurizing the glassware and blowing it up. And so that gas actually comes in, and it just goes into a piece of tubing. And this provides for the bubbling, and the multiple units there are actually then used to allow for approach to near saturation. Because what we don't want is if we're going to have gas flowing into a reactor vessel downstream, and we're going to have that for weeks or months at a time, if the typical gases, even if I was to be using something as simple as air, when you compress air, with a pump, what happens is that tends to drop the water out of it. And so even compressed air on a normal air compressor will normally be lower humidity than the surrounding air, and certainly not 100% humid. And so what happens then is that gas then goes through this sequentially, and that gives us then humidified air. Or we'll call it gas, because we've actually used this in multiple different ways. One is we've actually used for oxygen to increase the partial pressure of oxygen, to increase meristematic heterotrophic growth. We've also used CO2 under circumstances to alleviate ethylene action, but also used CO2 for photoautotrophic or photomixotrophic. That humidified gas, then from there, it actually went to then the manometer. And I want to explain this in particular here a little bit. I mentioned that there was a fitting there, and that white fitting then was nothing more than literally a tube. And then that tube was going down inside of another thin tube, and it's nothing more than a long test tube. And so in here, this is nothing more than sterile water. And what would happen is that if the pressure that's here, this pressure here, we'll call it the pressure at the T, okay? If that pressure is higher than the hydrostatic head from here to here, this pressure is equal to just hydrostatic head, which is rho times gravity times the h being the distance from there to there. Then this would start to bubble. Of course, that's what's happening over in the spargers and that. But we actually don't want that to happen. We don't want a bubble here. Okay. What we want to do is that this piece of tubing, if I expand this up and show this bigger, and then say that this is the connection to the T up here, and then it's going to the tubing here of the gas. Okay. Then the liquid on the outside will be here, and then just like you have a straw and you're blowing in it, not enough to make bubbles form. The meniscus will actually go down this far, and not the whole way to the bottom of the container itself. And so that is then literally, the pressure is another way that we measure very low, small pressures, is that we do that based on inches of water. And just to give you an idea, it turns out that 1 atmosphere is what we're under normal pressure in the room, if you will. And that is equal to 33 feet of water. So if 1 atmosphere, which is also equal to 15 pounds per square inch, PSIG, gauge pressure, okay, is equal to 33 feet of water, you can imagine that an inch of water is a very, very low pressure. And so the pressure that's actually then delivering then to this manifold, which could be very simple actually, you could actually take again like PVC plastic pipe and tap into that. And the idea then is that the flow rate that's then going through these filters, okay, there's going to be another pressure drop across here, the pressure drop here, and that pressure drop is going to be relatively large relative to the pressure here. So this pressure here and everywhere in this is going to be that same pressure as the pressure at the T itself. And then the pressure drop across there is now going to be the same for each additional filter that I place on there. And this is a filter, a typical filter. You can use a 0.2 micron syringe filter, for example. And for this application, we found that we don't have to use the specialized air vents. We can just use a standard 0.2 micron syringe filter made out of something like cellulose acetate, or probably better yet, since these are often autoclaved on the actual unit itself. If these were made out of nylon, for example, that would be fully autoclavable for connection to the actual bioreactor, which in this particular case happens to be a temporary immersion bioreactor. So what you can see then is by having it set up so that the controlling pressure is essentially the filters, then the same amount of flow rate will come out of each one of those. And if I put another unit on here, another filter on it, okay, as long as my total flow rate into here is high enough to maintain that pressure, then the flow rate out of each one of these is going to be equal. Equals F1 equals F2. And our goal, of course, was to actually then create a system in which we would actually deliver in a very cheap manner, not having gas flow meters or anything else like that, literally just by changing the pressure here on this regulator here, and through this barge change and balancing then to a certain target pressure of roughly 1 inch of water, H2O, as our target. That meant that all of this will then set up a reasonable gas flow rate, and these flow rates would be on the order of approximately 10 milliliters per minute. Okay. And the idea is that these low gas flow rates that are here were enough to actually come to the reactor itself. Okay, so we're going, in this particular case, I think that the configuration was set up so that the gas would come into the media reservoir. In this case, it was a media bottle. We just really like these media bottles because it turns out that a silicone stopper goes into there very nicely. I'm pretty sure it's a number 6 silicone stopper into a standard media bottle. Okay, and that gas could go into there and up into a tube, and that tube would be above the liquid level. And then this here would be the pressure would be the same as then another line that would go to the headspace, if you will, of the actual reactor itself. So we'll call this the actual reactor that has the glass beads in it that were in here, and the plant tissue that's inside here. Okay. And what that would do is that would actually come in at that point, and this is the air equilibration line. And so that just goes into the headspace, it's there. And then the last one here that goes into this is here is the liquid line. And the liquid line actually comes into the unit, and I'm just going to, for the sake of description, go around to the other side here. And this is the one that goes down into the actual glass beads on this side. So this is where the media goes back and forth when the reservoir goes up and down. And then this one here is where the gas goes back and forth. And so if you think about it, if you have a couple hundred milliliters of minute in here, milliliters, and this cycles, okay, and cycles and runs all of that 100 milliliters or so, let's say it's a 200, I think is a typical one that we might have. When we do that in a few minutes, the actual liquid flow rate into there is much higher than the gas flow rate. That's why we need this line here to allow for the air to move back and forth between these vessels when the liquid is cycling from one side to the other. And as I had mentioned before, we had actually placed in here pressure transducers. Okay, they were actually relatively inexpensive. But this was just experimental work where we could then interface that to a computer and measure then the pressure inside the headspace here. And that's how we did a live diagnosis to decide on which flow rates that were necessary in this particular configuration to maintain sterility. The only thing left then is that if the media is staying inside, and we have actually put ports in here that we could actually use for syringe additions or even sampling through that. And these are ones that we actually purchased that you can find that are for IV lines. And IV, I mean intravenous. I might have even spelled that close to right. Okay? And so, you know, basically a medical thing that's dripping into you in the hospital, they have ports in there, which you see the movies where the bad guy comes in to inject the poison into those ports. Okay, those ports actually are relatively inexpensive, and that does allow you to monitor things. It does increase additional contamination risk, and we cover it with foil and spray it with that. But for production purposes, we probably would not bother to keep track of that. Now, that allows us then one last thing, and that is where does the air leave the system? And that's why there's one more air filter here on the top, which is an actual polyvent, one of these air filters. And so the gas, if you'll put air in quotes here, because at that gas delivery, you're having the flow come into here at about 10 mils a minute, and then that 10 mils a minute is eventually leaving out here, and that's equal to F1. It's the same gas flow rate that's going through. And this flow rate can be set to a very low value because the rate of growth of the tissue in here is not enough to consume enough of the oxygen or generate enough oxygen if it was photoautotropic to alter that composition significantly. And so our goal is to try to use a very low amount of gas over very long periods of time to actually run the reactor itself. That really is a summary of the schematic, if you will, of the temporary immersion reactor. And with our goal being a configuration that could be implemented if you have photosynthetic growth and you don't have sugar, and potentially, let's say you wanted to 3 times a day raise and lower the reservoir, which we're currently doing with a computer. There's no reason why this could not be done manually. And then implementing this type of technology would be the idea for propagating then plants in an inexpensive way, where the components themselves are not that expensive, and for the most part, the only piece that is actually disposable is the plastic bag here that we've been using. Bag, which is really nothing more than an autoclave disposed bag made out of polypropylene. Because polypropylene is actually autoclavable. That's it. So hopefully then we'll catch a cycle of this that will happen this afternoon, and that will conclude the basic idea of the temporary immersion setup that we have configured here. I do have one more comment, and that is it's possible that you could actually raise and lower the reactor instead of raising and lowering the reservoir. And we had worked a little bit with that before, and we found it much easier to deal with the raising and lowering of the reservoir itself. The stepper motor has to be sized to handle the weight. We have actually used, for instance, plastic bottles before, because they're less weight and therefore the stepper motor can be simpler. But the advantage of using glass, of course, is that it's crystal clear and you can actually see inside to see if you have any problem with contamination. Okay, thanks.